Let's say I want to find the volume of this piece of foam. The top of the foam, we'll say, is a plane, has a certain normal vector. I can locate it on a set of XY coordinate axes, and I can trace out its base, which is a rectangle. At every point of this rectangle, I can let Z equal the distance from here up to that plane, so that Z of XY equals the altitude at the point XY. This is a rectangle, so it's going to have the form, let's say, A less than or equal to X less than or equal to B, C less than or equal to Y less than or equal to D. If we subdivide our X direction, if we partition our X interval from A to B, and similarly partition our Y interval from C to D, we'll get a typical ith X partition, a typical jth Y partition. Within that partition, we'll get a sample point xi star, yj star. Our altitude at xi star, yj star is our function z of xi star, yj star. The volume lying above our ij region is base area times altitude, altitude and that's just going to equal our delta x times delta y times z of xi star yj star. That will be our delta v ij. This expression is very similar to the expression that we would get if we multiply our area by a density, where we'd get a mass. Here we're multiplying our area by an altitude and we're getting a volume. If we know our altitude function, then we can easily perform the integral and find the volume of the region lying above this rectangular region of the plane. If we wanted to find the specific volume of this foam, we could measure its height, let's say at this position. We could assign an xy value to that position. We could measure its width, or length if you want, and width of this rectangular region, and get our inequality that describes the rectangle. We could as well put something flat here and arrange something perpendicular to that flat part of the surface and get its normal vector, at least estimate its normal vector, measure its normal vector. Alternatively, we could measure the height here and here and here, allowing us to conjecture a vector in this direction and a vector in this direction within our three-dimensional space, take the cross product and get a normal vector. That's going to lead us to the equation of the plane defined by this piece of foam. Now, I'm not going to write down an equation of a plane that actually represents this piece of foam, although that would not be difficult to do. But let's just say now that we have the plane x plus 2y minus 4z equals 12. Okay, now that plane defines a function f of xy, call it z equals f of xy, equals what? Well, if we solve this for z, we get x over 4 plus y over 2 minus 3. We might want to then find the volume beneath this plane for the region, and let's not say for, let's say above the region, 0 less than or equal to x less than or equal to 4, 0 less than or equal to y less than or equal to 3. That region could be sketched like so. If this is x and this is y, here's 4, here's 3, here's our region. On our typical ith x interval and our typical jth y interval, then the value of z equals f of xy above this interval, the volume of our chunk of foam or whatever it is we're trying to get the volume of, will be whatever we get when we plug the coordinates xi star, yj star into our function. And that's going to be what? That's going to be xi star divided by 4 plus yj star divided by 2 minus 3. Now that's not actually going to correspond to a volume above the plane. Let me change the 12 to negative. That'll change the 3 to positive. That'll change this to positive. And now for x in this region where x and y are both positive, we're going to have to get a positive z so we can really be talking about a volume above the plane. We can, of course, integrate a function over a region when the function does take negative values. That's not a problem, but we're not going to be able to interpret that as a volume in the context that we're considering right now. For this example then, we want to find started to write the word area. Okay, just swapped out that piece of paper. We want to find the volume beneath z equals f of xy equals x over 4 plus y over 2 plus 3, and above the rectangle 0 less than or equal to x less than or equal to 4, 0 less than or equal to y less than or equal to 3. From what we've seen here, we can pretty easily write down our volume increment. We partition, etc., and find that our delta V ij, our contribution to the volume from the ijth increment, is f of xi star yj star times delta x delta y. And that leads us to the total volume expression, sum from I equals 1 to n, sum from j equals 1 to m of f of xi star yj star delta x delta y. And without being too formal, we're simply going to assert that that approaches the integral, double integral, of f of xy dy dx, where our y interval goes from 0 to 3 because we partitioned the interval from 0 to 3, and our x from 0 to 4. It would now be easy to plug our expression for x in here and perform the integral. I'm not going to do that. Instead, I want to consider how we would find the volume of, let's say, this region. Now this has a triangular base, so it's going to have a triangular cross-section instead of a rectangular cross-section. That means that as we partition our x, as we move across our x-axis, our limits on the y are going to change because this triangle down here starts getting thicker and thicker. And we'll consider this problem in the next clip.